This video is going to answer a very important question, which is the question in blue. What is the slope of a curve? Now, why do we care about that question? We care about that question because we are studying constant acceleration, and in particular, this video presumes you've kept up to date with the assigned videos, and you know that when we have constant acceleration, we can look at the xt graph, the position time graph, for something accelerating. And that position time graph, the motion of something, also can be modeled by this equation. My position at any point in time, if I'm accelerating, is equal to my initial position plus my initial velocity times the length of time that I've been traveling plus 1/2 the constant acceleration I've been experiencing for that amount of time squared. In a previous video, we derived this equation, and since it's a t squared, we know that it's parabolic. So this question pops up because of the following. So let's follow the green. We now have a model for the position of something that's accelerating. We also remember from chapter 3 that the slope of my xt graph is the value of my velocity. So there's velocity information in this graph in the form of the slope of that graph. That tells me my velocity. We also know we're also very familiar with slope as rise over run, which is fairly easy to understand, hopefully, when you're talking about the slope of a line. If you have a line, its slope can be calculated by taking 2 points on the line itself and calculating how much you'd have to run and then rise to get from one point to the other, from the earlier point to the other, right? That's rise over run. So geometrically, this is a simple idea when you can see triangles like this. I see a run, I see a rise. Okay, the 2 points are on a line. Well, if we take this shape now, and we take this idea, what question pops up? I want to use the fact that slope of position time gives me velocity, but now I have a different kind of position time graph. I don't have a linear graph anymore, I have a curve graph. So this is how that question pops up. What is the slope of a curve? And frankly, that's, is it even definable? Can you talk about slope other than outside of a line? Short answer is yes. And the way we're going to get you comfortable with this idea is you're going to use your imagination, because I need you to imagine being able to zoom in on this line. Okay? First of all, one of the things about the line, the slope of a line, is that it's constant. On a curve, spoiler alert, we can define a slope, but it's not constant. And the reason it's not constant is how we look at rise over run. If you have a curved shape, so here's where you're going to start using your imagination, okay? When you stand far away from the curve, and just look at it, like step back and look at the curve is obvious. It looks something like that. And it's hard to see, if you do just rise over run on this, there's a problem, right? I could pick this point and this point, and I could do rise over run. And you could see that that's a certain ratio. But what if I pick a different pair of points? What if I happen to pick this point and this point? You can see that my rise is greater than my run. Over here, my run was bigger than my rise. So defining rise over run, the answer you get, the number you get, if you could take these measurements and get a number, the number changes depending on where you are on the curve. So that alone gives us our first, in terms of what is the slope of a curve? It's not a simple answer. There are certain characteristics of the slope of a curve. This shows that the first thing that the slope on a curve does is that it changes. So it varies. Right? If you think of slope as like how steep something is, well, hopefully qualitatively you could see in the early part or the beginning part of this curve, it feels kind of shallow. And as you move farther to the right, the curve gets steeper, right? If this was a hill. So the slope changes, or it can change. Well, on a curve, it definitely changes. Also, the numeric value, the actual value of the slope. So now I'm talking about like a calculable number. The value of the slope depends on the location, on where you are. Where on the curve you're measuring the slope. Okay? So for example, when I'm on this part of the curve, my slope seems less. When I'm on this part of the curve, my slope seems more. Okay? The other thing we're going to need to appreciate as far as what's the slope of a curve is really like how it's defined. And what do I mean by that? Well, you see how this on the green, the green triangle here, is that really a good a calculation for the slope of that curve in this region? Or, well, first of all, when I say where, the key thing actually is this where means at what point. This really means point on the curve, not a region, but a point. If I looked at it as a region, even within this area, I hope you can use your imagination, the steepness varies even within the green triangle. So on this part of the green triangle, where the curve is still kind of shallow, it's shallower here than over here, right? So that's, you could see how defining the slope of a curve really depends on what part of the curve you're looking at. And to be super precise, I could pick different points on a curve and go, well, if I'm over here, it's pretty shallow. Over here, it's less shallow. Over here, it's less shallow. In other words, it's getting steeper and steeper as I go along the curve. So what we really see is that the slope changes depending on which point you're at on the curve, not some region, but literally from one point to the next. At every point that I move forward to the right on the curve, it's getting steeper all the time. So how can we get a sense of what this is without using calculus? For those not taking calculus, spoiler alert, this is what calculus does. One of the main things in calculus is it determines slope of curves, of any function, really. Okay, so how are we going to do this for non-calculus physics, or get a sense of that? Well, one way to get a qualitative sense of it is to zoom in on that curve and realize that if I zoom in on that curve, so I'm going to draw I'm going to step back, I'm going to look at the curve, and then I'm going to zoom in. So I'm going to go over here, and I'm going to really zoom into a tiny, basically a point. But now I'm going to expand that point. So just follow along real quick. If I expand that point, if I zoom in on it, hopefully you realize it's almost like if I zoom in enough, that point looks like a line, or that region of the curve looks like a line. But it's really tiny. It's a really, really tiny segment. And if I do that, now I can get a delta, a rise, and a run. Okay? But if I take, so this rise and run is definable, right? I mean, I could get real numbers. So I can get the slope. Now, but I got this line by really zooming into that. So if I take this line and now, using your imagination, shrink it back to a point, the numbers are still there. They're just really tiny. We can't see them. Okay? The end game is that if I take this and I shrink it down, what happens is this slope corresponds to the slope of a line tangent to the curve at that point. What? All right, let's redraw this. So if you have trouble believing what I just said about as far as like using your imagination to picture what's going on, that's okay. If you're not sure, just come in for 5 minutes and talk to me for 5 minutes. I'll explain it a little more clearly. But if that made sense, so I zoom out, I zoom into the curve so that I see a line segment, even though it's curving the whole time, but I get so close that it's basically a line, and I can calculate a slope. Now, if I do that, so here's that little part of the curve, and I calculated my slope, and it's really tiny, so it's just a little tiny triangle, but I have a slope. But that part is where I figured out that slope is for a very, very tiny, is for a point, say on the curve, right? Something like that. Well, if I take a look at that slope, it turns out the slope of the curve at that point is the same as the slope of a line that touches the curve right at that point. Okay? So this is how we could describe the slope of a curve. The slope of a curve, so here's the end game. Slope of a curve. What's the nature of that? First of all, the slope of a curve changes. It's not constant. But the slope of a curve, so I have to define, if I'm going to ask about the slope of a curve, I have to say, where am I on the curve? Slope of a curve at a point on the curve is equal to the slope of a line tangent to the curve, and we'll close with a little confirmation of what tangent means in case we're not sure. Slope of a line tangent to the curve at that point. Tangent means what? Tangent means the line intersects the curve only at one point. It doesn't pierce the curve. So at that point, this is not a tangent line. It punches through the curve. In other words, one line is inside the curve and one line is outside the curve. So that's not a tangent line. This is not a tangent line because it touches the curve at 2 points. A tangent line touches the curve only at 1 point. And mathematically and geometrically, if it's tangent, you give me any curve and a point on that curve, there is one and only one line that's tangent to that curve. And that is the slope of a curve.